As we said earlier, water is one of those few elements that exist in all three physical states on the planet, solid, liquid, and gas. One of the really important properties for water is that as a solid, aka ice, water is less dense. So it floats. Okay? When water starts slowing down because the temperature is dropping, the molecules vibrate less. As the molecules vibrate less, those hydrogen bonds become more and more stable. You can see over here in liquid water, we're depicting those molecules moving very quickly. And if they're moving quickly, they're moving fast enough that they're overcoming those weak hydrogen bonds. Hydrogen bonds aren't strong like covalent are. They're strong enough that collectively, they create surface tension so that when you belly flop, it hurts. But overall, they're relatively weak bonds. But as those molecules cool down, as they release that heat, and remember, heat is kinetic movement. So when we release heat and those molecules slow down, those hydrogen bonds, as seen here, become more and more stable. As they become more and more stable, the water molecules spread out into a lattice. Okay? That's actually creating more physical space between the water molecules than when they were in their liquid form. Therefore, ice is less dense. And this is important biologically for a couple reasons. One, because that ice, as it freezes on the surface of a water, ice acts as an insulating layer. So that life below can still continue. It doesn't get quite as cold below that layer of ice because that ice is actually insulating the water from releasing more heat to the environment. Okay? And this allows life to continue underwater. Okay. Could you imagine if everything in lakes or ponds died every year? And that's just not the case. The other thing is, it's good that ice floats because it freezes from the top down of a water mass. And that means that life can continue. If we froze from the bottom up, we'd push the life up and up and up, and then eventually everything would die again because there would be no water. So the fact that ice freezes and then floats is really important to maintaining these ecosystems year-round. And last but not least, water is considered the universal solvent, the solvent of life, meaning that it doesn't only dissolve negatively charged particles, but it can also dissolve positively charged particles. Let's see if we remember what those are called. If you have a positive charge and you're an ion, you would be a cation, and negatively charged ions are anions. And water can dissolve all these things. Water can also dissolve anything that has a bit of polarity to it. So for example, glucose isn't really a charged molecule, but it attains a slight charge in water, and it is able to dissolve in water. This is why when you mix sugar into a glass of water, it dissolves, it spreads throughout. Okay, so it has to have some kind of slight charge. It has to have areas that are maybe a little bit polar. And if it has that, the water molecules can break it apart. Water's a really big bully. Water can get in between ionic compounds and really bust them apart, bust them up, due to it has both the negative charge on the oxygen and the positive charge on the hydrogen end. So let's just check a few things. You should be able to explain the saying, it's not the heat, it's the humidity. So why isn't it the heat that bothers you? Why is it the humidity? Think back to evaporative cooling and what a high humidity in your environment would prevent. Okay. Next, how can the freezing of water crack boulders? For this one, consider what happens to the water molecules as they slow down, as the temperature decreases. What happens to the spacing between the molecules? How would you make a 5 molar solution? Okay. Recall that this capital N means molarity. And a 1 molar solution would be 1 mole of the substance dissolved in 1 liter of water. Okay, so in order to solve this problem, the first thing you need to do is calculate the molarity, or the molar mass of sodium chloride. And I've helped you out a little bit here by giving you the atomic mass of these two elements already. Once you figure out the molar mass, then you know that that amount of substance divided in 1 liter of water would give you a 1 molar solution. So then how would you create a 0.5 or a half molar solution? Finally, take a look at this question. A water strider's legs are coated with hydrophobic substance. What is the benefit? Remember that hydrophobic means afraid of water. So this is a water fearing, something that repels water. Hydrophilic would be water loving. Consider what things water likes to interact with. Consider its nature. Water is polar. It has a partial positive charge, a partial negative charge. Therefore, it likes to interact with other things that have some sort of charge to them. Make sure that you take a chance and answer these questions, and then consult Appendix A in the back of your book to check your answers. Now, water also does something kind of peculiar. Water exists as this H2O molecule. But due to those attractions, due to those hydrogen bondings that happen between the oxygen and the hydrogen end, water doesn't stay completely faithful to itself. It can dissociate, meaning that parts of it come apart. And this is a reversible reaction, and there's this constant balance. So most of the water in a glass of water exists as H2O. But also within that, and equally balanced if we're talking about pure water, we have both the hydronium ion, H3O+, and the hydroxide ion, OH negative. Hydronium ion being the cation, the hydroxide ion being the anion. So what's happened when we say dissociate is that the hydrogen atom of one of these molecules has become unbonded, uncovalently bonded from its oxygen molecule, and has attached itself to another water molecule, creating that H3O. Okay, becoming that H3O. And small amounts of molecules are always doing this in water. When the hydronium ions and the hydroxide ions are in perfect balance with one another, we say that the solution, or that the water, is neutral. Okay? We say that it's neutral, that we have this perfect balance. Sometimes you also see the hydronium ion depicted like this. Okay? The solution is in neutral when they're in perfect balance. And now we're starting to talk about the pH, the potential of hydrogen. So let's take a little bit of a closer look at pH. So if we're talking about pH, then we really need to consider the pH scale over here. Just taking a quick look at our pH scale, we can see that it ranges from 1 to 14, and this pH is really the potential of hydrogen. It's measuring the concentration of hydrogen ions in solution. Okay. So anything less than 7 is considered an acid. Anything greater than 7 is considered a base. Okay. And you see here that pure water, again, is neutral because the concentration of ions is equal. This is an important idea right here, that we're not saying that an acid has all these hydronium ions and that's it. There's still a balance of hydronium and hydroxide ions in there. It's just that if you're acidic, there's a lot more hydronium ions. If you're neutral, the hydronium and the hydroxide equal out each other. And if you're basic, you have a lot of these hydroxide ions. Okay? And you have a lot more of them than you have of the hydronium ions. You'll notice too that there's a few items that are found in the human body here. So you'll see that urine is slightly acidic, human blood is slightly basic, and yet these things are both still hovering around that neutral mark. Now, that's important for a few reasons, but you really are maintaining homeostasis in your body, and deviating extremely from this is going to cause problems. You'll see that we stay right around neutral for most areas in the body, except places that are really compartmentalized and have specific functions, like your stomach. Your stomach has a really low pH. It's very acidic. It's a pH of 2. Okay? And the reason for that is that that low pH makes the breakdown of different chemical components, different things that you eat, much easier for your body to do. And that's the beauty of having specialized organ systems, in that we can change the different kinds of conditions that are found in these different places and really maintain homeostasis in the rest of the body. Okay. pH is really known as the power of hydrogen. We're measuring that hydronium ion concentration there, and it's that balance between the two. Okay. So anything that's considered an acid is going to contribute the hydronium ions into solution. And anything that's considered a base contributes hydroxide ions. Should be a negative there, please. Into solution. So, difference between acids and bases there. Remember, it's a balance between the two. And even in neutral and even in pure water, it's a balance between the two because water does dissociate back and forth between those. As long as it's in balance, you have a pH of 0 there. One last item to consider when we're talking about pH is the idea of buffers. So what is a buffer? Well, you can imagine that it would be bad for your body to deviate extremely in its pH. So if you ate something really acidic, you wouldn't want the pH of your body to change. You want to neutralize that and bring it kind of back to a set point. And there are a variety of chemical reactions in your body that either contribute hydronium ions or contribute hydroxide ions. And it's an important feedback mechanism. One of the ways that your body controls your respiratory rate, the rate at which you're breathing, is by detecting the pH of your blood. Okay? And when that pH changes from the carbon dioxide present in your blood, it triggers your body to breathe more rapidly to get that carbon dioxide out of your blood and get more oxygen in. So really fine-tuning and regulating pH is really important. So we don't want it to deviate incredibly because then we have problems with our systems. And that's where buffers come into handy. Okay? A buffer is something that resists a change in pH. And it does this by either contributing or donating hydronium ions. Okay, so it either contributes or donates those hydronium ions, and that way it can resist change in the system. Okay, so a quick few things to check. Based on what you know about pH from your reading and from some previous knowledge, if you have a solution and it has a pH of 9, and then another solution has a pH of 4, what is the difference in that concentration of hydrogen ions? What's going on here? Take a second and consider that. Recall that every change in the pH, every difference in number from pH to 9 to 8 to 7 to 6, each of those represents 100 times change, right? It represents that distance. It's not a change of 1, it's a change of 100. So between pH 9 and pH 4, okay, I have 10 to the 5th, or 100,000 times as many hydrogen ions in something that has a pH of 4 than something that has a pH of 9. Okay. So sometimes you'll also be given the molarity of a solution. So if you have a pH, you want to figure out the pH of a solution, what we need to do then is consider how many decimal places this is. Remember that molarity is calculated by the molar mass of the substance divided by 1 liter of water. So I want to figure out what the pH now is of a 0.01 molar hydrochloric acid. Well, 0.10 molar, I had to move the decimal place over 2 places to the right so that I have a molarity of 10 to the negative 2, which means that I have a pH of 2. If you have questions on any of these, make sure you stop by and check in with me.